Today we're going to discuss functions. Now, functions, as you're familiar with them, are probably defined by something like a formula. Right? That you give an input x, and then the formula tells you how to compute the output of the function. So the characteristic property that a formula has is that for an input, there's an unambiguous output, and the rule for computing the output is given by that formula. So informally, then generally, a function is just any rule whatsoever that assigns an unambiguous output to an input. And so it doesn't have to be a formula that applies to numbers. You could just have any input and then an unambiguous way of associating an output to that input. So that's what it is informally. And if the x that the rule applies to, if that lives in a set A, and the outputs y live in some set B, then the data in the function is just that input-output pair xy. And that makes us think of a relation based on what we've done recently, a relation between the sets A and B. So that leads us to our formal definition of a function. So a function on a set A is just going to be a relation, and we'll just write that relation as f, and it's a subset of that set A crossed with another set, B, with the property that, and this is the unambiguous rule part, so there has to be a quote-unquote rule defined for every A in A that gives you an output, and that rule has to be unambiguous. So that means for every A in A, there is exactly one pair of the form AB in this relation set. And so for every A in A, you have to have a pair AB. So that's telling you that A is the output for your input A, and there's exactly one pair like that. Right? So you can't have AC for some C different than B. There has to be an unambiguous rule associating A to B, is the way we interpret this inclusion of AB into this relation F. And when AB is in F, then we adopt the notation that we're used to, that F of A is equal to B. Those are just equivalent ways of saying the same thing. And that set A, that is called the domain of our function F. So let's take a look at an example to see that the features of this definition are making some sense. So here's a familiar function that you would be used to working with from calculus. F of x equals x squared. And so you think about this as a formula. It's a rule that tells you when you input an x how to compute the output. Okay, and we want to understand this in terms of the definition, see how this is intelligible in terms of the definition we just gave. Right. So we'll understand this as a formula that applies to real numbers. So we can take our domain to be equal to the real numbers. And of course, the output is also going to be a real number. So we might take our set B to be the real numbers as well. So what we're looking for is some set of pairs xy in R cross R. And so this is going to be our relation set, and so which pairs xy should be in this relation set? Well, you want to think about this y here as being the output of this input x, right? So when is y there the output of that input x? Well, it's the output when y is the output when y equals x squared, right? So this is the set of pairs xy in R cross R such that y equals x squared. Right, so you just use the formula and you can encode it in this way to create the definition of your relation set. And so if you're given some formula, you just use that formula to say what the second coordinate is in terms of the first. So one thing you might note about this set, note that the set F is literally the graph, or maybe I should say literally what you would usually think of as the graph of f. Because we can graph this set in R cross R, or R squared, R2. So you got like an x-axis and a y-axis, and this is just all of the pairs that lie, right? So for a given input x, like, let's say, let me label some things, 1, 2, 3, 4. For the point x equals 0, y has got to be 0 squared. That's 0, right? So 0, 0 is in the set f, and 1. Well, if you input 1 for x, then the output is 1. So 1, 1 is in the set f, and you input 2, and you get 4. And you could do this for the negatives as well. And you sort of imagine connecting the dots there. What you find is that this is the set f, and that's what you would normally think of as the graph of f in calculus. So basically the set theoretical so the set theory definition of a function identifies the function with its graph. So that's the basic intuition for this definition of a function in terms of sets. It's just that all the information about a function, the way you're used to thinking about it, is just contained in the graph of that function. The second thing you might want to note is that if we change the domain A from the real numbers to something different, we get a different function. So, for example, we could take A to be the set R greater than or equal to 0, which is the set of x in R, such that x is greater than or equal to 0, so the non-negative real numbers. And then our function is different, because the domain of the function is baked into the definition, and you can just see that from the graph. I mean, we could write it down. So this would be f. So if that's your a, that would be f such that xy is in R greater than or equal to 0 cross R now, such that y equals x squared. And this is a different set because before you were allowed to have x's which were negative, and now you have x's, you're not allowed to have x's which are negative. And the graph reflects that. So if we draw a picture of this set in R cross R as we did before, then of course we just get the right half of that parabola, so we just get this. Right, and so those are different sets. So this is now f in this case. So the basic point to make is that even though we have the same formula, so same formula does not necessarily imply, doesn't imply the same function. Right? The domain matters. And you might like to summarize this in the phrase, formulas aren't functions. Right, so functions are more than just the formula, okay? Because we have the same formula, y equals x squared here as we did before, but we have a different function because we have a different domain. On a very distinct note, we can in fact change the set B and still have the same function on A. So for example, if we again go back to A being R and now take b to be r greater than or equal to 0, and we still have our f of x equals x squared. This is actually the same function as the one we started with. So this is the same function as the original. And that's because, so our original set was f was the set of x, y in r cross r such that y equals x squared, right? But if y equals x squared, then y is non-negative, right? So this is exactly the same as the set of x, y in r cross r greater than or equal to 0, such that y equals x squared. So, and again, we can draw the picture. So before we had the negative y-axis in the picture because we were considering b equal to r. But now if we just cut off that picture, so our entire picture is above the x-axis here, right? We haven't cut off anything from the graph, and because the graph lives above the x-axis. So again, this is our f. It didn't matter that we cut away some of that b because we didn't cut away any of the relation set that defines f. In fact, so there are many sets b that would give the same function with the formula f of x equals x squared and domain a equals r. Right, so you could do something like, you could say b is equal to maybe the non-negative real numbers and then union the interval from, from -1, or I guess I should say negative infinity to -1. The interval from negative infinity to -1. Right, because the picture here looks like, so let's say if this is -1 here, then we sort of deleted, oops, my eraser is too big there. You deleted that stuff in the middle. And so if this is the x-axis, this is the y-axis, this is at -1 here. Oh no, I just put it back. What happened? Yeah, we want to delete that stuff. So everything in blue here has been deleted. So our domain is everything that's our B set is everything on the y-axis that isn't in blue, and then so our A cross B is everything in this picture that's not in blue, and then we still have our graph here, which is unaffected by removing that blue stuff between. With y coordinate between 0 and strictly between 0 and -1. So basically any set B, so any set B which contains r greater than or equal to 0 would give us the same function. So to emphasize that functions don't have to be given by a formula, let's just look at a situation where we have some sets with basically just nonsense names, just variable names. So our sets just contain A, B, C, and D, E, F. And we can create a function here. All we have to do to create a function, so we think about it as a relation, so we can just use a diagram to indicate the relation initially. And we just have to, for each thing in the domain A, we just have to say unambiguously where that A is going to go. So for example, I could just say that A is going to go to D, and for B, I could also send that to D, and for C, I could send that to E. Right? And this defines a relation. So so let's write down F as a relation set. It's the set AD, BD, and CE. And the definition of function is satisfied here. For everything in A, there is a pair containing that element of A as the first thing. So we have A, B, C here all represented. And there's a unique one with that element as the first thing in the pair. Right? So we have AD here. We don't see an A something anywhere else. And we don't see a B something anywhere other than here. And we don't see a C comma something anywhere other than that third element. So this is a function from A to B. And this is contained in A cross B. Notice there's not really, those are the only requirements you have to check depend on really focusing on A, not so much on B, right? So the fact that there's nothing, there's no arrow into this F here, that doesn't matter at all. And the fact that there's two arrows coming into D, that doesn't matter at all either. Right? Perfectly good function. We could also represent this function instead of in a diagram with arrows or as a set like this. We could also try to draw a graph of the function. So the graph of our function, we'd have, the graph is this set of points. I mean, the graph is this relation F. And we could represent that in a horizontal vertical fashion. So our points from A are A, B, C, sort of along the x-axis, quote unquote, and then on the so-called y-axis, we have the points D, E, and F, D, E, F, and then for each of those, so for each pair of points, we have A, D, A, E, A, F, B, D, B, E, B, F, and C, D, C, E, C, F. So the graph of our function is the points, makes the points AD, and we have B, E, BD, and CE. And so you might kind of indicate them by something like this. Okay, so the graph is really just these 3 points. So just draw on the connecting lines to make it look a little more suggestive. And I just want to reemphasize one more time that our function f here, we could also represent f by the diagram, by diagrams like this. So there's A, B, C, and we could just leave off the point F, right? So if we leave off the point F, so this set now, this is a different set. So maybe we could call this set here, so we could say B prime with D and E, right? But the set F, the function F is still the same. So F is still the same as above, right? Is the same. Because F wasn't involved as an output of the function. So we can change the set B, we can reduce the size of it as long as we're not cutting out anything that's an output of the function. Right? And so this F would have the graph. So if we do A, B, C, and then we have just D and E. Then again, we'd have this point, this point, this point. right? So we see the graph is still the same. So these are actually the same function. Right, but we can't alter things in the domain. You can see here if you remove A or B or C from the domain, then you're going to remove points on the graph. So they would be different functions. Here's an example of a relation that is not a function. So you can have relations between sets that are not functions. It has the diagram shown there, and so we can write down the set for this relation. It has A, D, A, E, and B, E in it. Right? And so this is not a relation for two reasons. So the first one is that the rule for where to send A is ambiguous, right? So there are two elements of R of the form A comma Y. Right, so with first coordinate A. And that violates the definition of function. So for every A in little a in capital A, our domain, there's supposed to be only one pair with that A as the first coordinate. And two, there's no rule for where C goes. Right? So there is no element of R of the form C comma Y. So a function is supposed to tell us where everything in our domain goes, but this relation doesn't express where C goes, so this cannot be a function. So we've seen if you have a function on A, and it's a subset of A times B, then to some extent you can change B and not affect the function. And so it can change B to some extent and not change F as a function on A. But you can't make arbitrary changes to B. For example, let's say AB is in F. Right, is in F. You can't remove B, this little b, from big B. Right? So you can't take B prime and define that to be B minus B, minus the point B, without changing the function, right? So now it's no longer the case. So F is not contained in A cross B prime, right? Because F has the point little a little b in it, but B prime does not have the point little b in it, right? So this set F is now not contained in A cross B. So basically what we see from this is that the B, such that there's an AB in our function F, those B are important. And that's the content of our next definition. So if a function F on a set A is given by the relation F contained in A cross B, the range of F is the set. So we'll use the notation, so it's a set it's denoted f of a. It's contained in B, defined by, so f of a, this is the y in B, so it's the points in B such that y is equal to f of x for some x in A. Okay, so it's just like up here, the b's such that AB is in F, right? Such that there's some A here where f of A equals B are important. Okay, so that's the set we're singling out here. The points in B that are f of something in A. So basically, what you can think of, so basically f of A is the smallest set B such that f is contained in A times B. And if you try to remove anything more, so basically f is contained in A times f of A, and if you try to remove anything more from f of A, then your function f is no longer contained in that a times the set that remains after you've removed something from f of A. Okay, so in the definition of a function, your b, so in the definition of function on A, you can take B to be any set which contains the range of f, to be any set such that B contains the range of f. Because if you add those extra points in, I mean, they sort of don't affect anything because you're not adding any points to the graph, because you're not adding any points you're not adding any points into the set B which are getting hit by the function. And so basically the range is all of the things that are getting hit by the function, that are outputs of the function. You can add extraneous stuff into this set on top of that without affecting anything. The basic point in total is that when you define a function on a set A, this set B can be any set whatsoever that contains the range of that function f. And so all you have to do is contain all of the possible output values you're talking about, and that would be a suitable B. But it can be somewhat annoying to have this B have this kind of variable nature to it. So it is useful to talk about situations in which this set B has been specified concretely. So we'll make another definition. A function from A to B is an ordered pair. Or maybe I'll say a function f from A to B is an ordered pair of a function and a set B, where f is this relation contained in AB. So f contained in AB is a function and A and B are sets. Okay, so we're just taking our function and we're adding in just one extra piece of information to say where the outputs of our function are going to definitively be thought to lie. And so this is written in that way. And so you could read that something like f maps A to B, or f takes A to B. And in this scenario, B is called the codomain. So B is the codomain of the function. So one way you can think about this new definition, how it contrasts with the last one, is that in the last one we had a function defined on A, and it sort of didn't matter what the set B in the A cross B was, as long as it contained the range of our function f, then it was fine, because that didn't affect the graph, which is what we were sort of identifying our function f with. So in that case, you could have one function considered as a function from A to B, and another function, say, considered as a function from A to C, but those two functions could be equal to each other. In this new definition, now we have a function from A to B, and being this ordered pair, you have to have the same B in order for two functions to be considered equal. So they have to have equal domains and codomains in order to consider your functions to be equal. So that's kind of the difference. So this definition cares about what the codomain set is, whereas the first definition doesn't. So let's think about another example of a function. So we can consider a function from z squared to z. And let's say it's defined by phi of mn equals 6m minus 9n. And so as a set, this is the set of, so we have mn in z2, so it's pairs with mn in z2, and then we have p in z, so this is in z2 cross z, such that p is equal to 6m minus 9n. Okay, so that's how we can write the function as a set. And so this set clearly has the domain is z2 and the codomain is z. And let's try to figure out what the range of this function is. So the range, remember, so that would be phi of z2. Right, so this is all of the p in z, such that p is equal to 6m minus 9n, where m and n are integers. And so it's all the p that are in the image of that function. And what you can note is that p must be divisible by 3. So note 3 divides p, so p must be a multiple of 3. But in fact, we can get all multiples of 3. So basically 3 divides p, that implies that phi of z squared, that's contained in the set 3 times z, which is all of the multiples of 3. So this is all of the k and z such that 3 divides k. And then we claim that the other inclusion is also true. So we claim that 3z is also contained in phi of z squared. And so for that, it just suffices to see that 3 is in phi of z squared. So proof 3, so if we take that's in the set 3z. That's in phi of z squared, since 3 is equal to, let's see, if we take n equal to -1 and m equal to -1, that's 6 times -1 minus 9 times -1. Right? So 3 is in the image there, and then all we have to do is to get any other element of 3z, so any other element of 3z is of the form 3L, right? So that's 3 times L, so we can just take this equation with 3 and multiply it by L. So thus 3L equals 6 times -L minus 9 times -L. And that is equal to phi of -L, -L. Okay, so that is also in the image set. And so that implies, so thus we conclude that this 3z set is equal to phi of z squared. So that's the image. Okay, so we could also, right, so we could thus use phi mn equals 6m minus 9n to define a function phi from z squared to 3z. So I want now to think about function from a to b generally, in general terms. So what defines, the defining characteristic of a function is that whenever there's an a over here in a, in capital A, that there's got to be a single output for that function, right? Single unambiguous output. So this b equals f of a. So every time there's a little a in a, there's an arrow and exactly one arrow coming out of it, right? That's representing this pair AB in the relation that defines f. But it could be that that there is another a, so there could be an a prime here that maps to that same b that a went to. Right? So while on the A side of things, you only ever see one arrow coming out of A, right? You can see multiple arrows coming into B. And so you can see 2 or 3 or even more, right? So there might even be an A double prime that goes to that same B. So you can see multiple arrows coming into a B, and also you could see no arrows coming into a B, right? So there might be some B prime here which has absolutely nothing coming into it. So it turns out to be very convenient to have vocabulary for when these two things do not happen. Okay, so we'll look at a definition. So one, a function from A to B is injective So injective is going to be when the first thing we talked about doesn't happen. So when there's not multiple arrows pointing into things in the codomain, right? So when you have a little b in your codomain, capital B, that there's not multiple arrows pointing into it. So probably the easiest way to say that is that for every little b in your codomain, there exists a unique a such that f of a equals b. But it turns out that there's a better way to phrase that. And it starts by looking on the a side of things. So what we're going to say is that it's never the case that you see two A's, right? Like your A and your A prime. It's never the case that you see two different A's coming into the same thing. Okay, so that's the basic idea of the definition. So is injective if A1 not being equal to A2, and so A1 is in A and A2 is in A. If they're not equal, that implies that f of A1 is not equal to f of A2. And so when you take two distinct things in the domain, that they end up in distinct places. They never converge to the same place. Right, so yeah, so I guess I'll be cleaner about this for all A1, A2 in A. And I'll just formulate this contrapositively because that actually turns out to be the most effective way to use this definition. So contrapositively, if f of A1 being equal to f of A2 implies A1 equals A2. Okay. 2. F from A to B is surjective. So that's the situation where so what we want to say is this is going to be the situation where there's no lonely B prime like we had in this picture here. So is surjective if for any B and B there exists an A in little a and big A such that f of A equals B. And 3, f from A to B is bijective if it is injective and surjective. Okay, so basically injective is everything gets hit only once. Is that everything gets hit no more than once. All right, surjective is that everything gets hit at least once, and then bijective is that everything gets hit exactly once. Okay, so injective, there could be some things which are not getting hit, but if you do get hit, you only get hit once. Surjective means that you're definitely getting hit, but maybe you're getting hit more than once, and bijective means that you're getting hit exactly once. Everything in B gets hit by something in A exactly once. So let's turn to some examples. F from R to R, defined by f of x equals x squared, is neither injective nor surjective. So not injective. So why is it not injective? Well, injective should mean that everything gets hit once, right? But for example, 1 squared and negative 1 squared are both hitting 1 as the output. And so 1 equals f of 1 and f of negative 1. Right, so you have two things that are not equal, but their f's are equal. Their f values are equal. And not surjective. So f of A equals, say, negative 1 is not satisfied for any A. It's for any A in R. Right? You can't square any real number and end up with negative 1. So negative 1 is not getting hit. Okay. As an add-on to this example, you can say that, however, if we consider f as a function from R to the non-negative real numbers defined by the same formula, this one is now surjective, so is not injective but is surjective. So not injective, that's the same as before. Same as above. Now the surjective, given any y in the non-negative real numbers, right, in the codomain, what you can do is, well, so we're basically looking to solve the equation. So we're looking to solve the equation, right? So we're trying to solve f of x, which equals x squared, equals y, right? We want to find an x which hits that y. And so looking at this, we see that since our y is greater than or equal to 0, we can take the square root of it. Okay, so we see that f of square root of y equals y. And square root of y is a real number since y is greater than or equal to 0. Okay, so any non-negative real number gets is in the image of our function, gets hit by our function. And so basically we just altered our original example of f as a function from the real numbers to the real numbers. We altered it by changing the codomain to be the image of f. And so basically what happened here, we can just sort of note, we can alter the codomain of any function to make it surjective by taking b to be the image of a under our function. So let's take a look at another example. So let's consider the function defined on the non-zero real numbers, r star, so r minus 0, to r minus just the point 1, defined by f of x equals 1 plus 1 over x. And so the claim is this is injective and surjective. Well, oh, yeah, I don't know why I'm... All right, we have perfectly good terminology for that. So this is bijective. Okay, so the injective part. So injective, the most useful way to prove injective is contrapositive, because it allows you to start with the equation f of a1 equals a2 and then try to prove that a1 equals a2, rather than starting with the negation of the equality. So you actually have an equation to work with. So suppose f of x1 equals f of x2. And that's just equivalent to 1 plus 1 over x1 equals 1 plus 1 over x2. Then by subtracting 1 over x1 equals 1 over x2. And then you could either, say, invert both sides of the equation or multiply by x1 times x2 on both sides, which is equivalent to... equivalent to x1 equals x2. Right, so starting with f of x1 equals f of x2, we conclude that x1 and x2 are equal. Right, so those potentially different x1 and x2, which go to the same thing under the function, they were actually equal. Okay, so that's what our injective... So that's how you do an injective proof. And the surjectivity, so what we have to do is, so let y be an element of the codomain here. So basically you're trying to show that this codomain is the range by showing that anything in that codomain gets hit by the function. So what we're trying to do, so basically what you do is a little bit of scrap work. So we're trying to solve y equals 1 plus 1 over x, right? And so what we can do is that's equivalent to 1 over x equals y minus 1, right? And so x is equal to 1 over y minus 1. And so we can take this as our thing. So you just choose that as x, so then letting x equal 1 over y minus 1. And so now that I have that, I don't need all that stuff. We see that. So you're just trying to show now that f takes this x to that y that you started with. We see that f of x, which is equal to f of 1 over y minus 1, that's 1 plus 1 over y minus 1. And 1 over y minus 1 is just y minus 1. And that is just y. Right? So that y we started with got hit by our function, and so we have the surjectivity. And so injectivity and surjectivity, that means bijectivity. So one thing we're familiar with about functions from, say, calculus or algebra is that when we have two functions where the codomain, so where the place where the outputs land of our first function f is the same as where our function g is allowed to have inputs, we can do those functions in succession. Right? So we can do f first to take a into b, and then g to take b into c. And so we can formalize that here. So here's a definition. So suppose f is a function taking a to b, and g is a function from b to c. And let's say they're defined by the relation sets in A cross B and B cross C. The composition of f and g, denoted g composed with f, right? So it's f first, so follow the arrows, f first, then g, is defined by it's g composed with f, and it's a subset of a cross c. Right? So we're taking inputs in f and we're going to land in c. So we want x comma z, say, in a cross c. And what is this? Well, the z is something that got, so you have to imagine in your picture, so think about it in your picture up here. So you have z here in c, right? So there's your z. So when is that a result of this composition? Well, when that z got hit by some y over here, right? So y, let's say you have a y over here, and that y hit z when you apply g, and when that y came from f, right? So when there's some x over here that hit that y, right? So you have to have this, so your x and z are in there when there's some intermediate y, right? So that when you applied f to x, it ended up at y and b, and then that y ended up at z after you apply g. So that leads to our definition here. So it's x and z in a cross c such that there exists a y in b with y equal to f of x and z equal to g of y. Okay. And that is just the set of, so z is equal to g of y. And so if you take this expression for y here and you plug it into there, right, we see that this is just the set of x comma z in A cross C such that Z equals G of f of x. And maybe a more succinct way to write that is just it's the set of x comma g of f of x, where x is in A. So this basically tells you when you have f and g defined by formulas. So for example, if let's say f from R to R is defined by f of x equals x plus 1, and g from R to R is defined by g of x equals x squared plus x, then when we do g composed with f of x, right, we really just have to do what we are used to doing from pre-calculus and calculus. You do the g of f of x, right, which is what we had right up here, g of f of x, and that's, well, f of x is x plus 1, and then we just plug that into g there, and we have x plus 1 squared plus x plus 1, which we could expand out if we felt like it. For a less formula-based example, we can consider A to be the set with A, B, C, B to be the set with 0, 1, and C to be the set with 1, 2, 3. And let's let f be the function that sends A to 0, B to 1, and C to 0, while G is the function that sends 0 in B to 3 in C, and 1 in B to 1 in C. So this is contained in B cross C. This is contained in A cross B. Okay, then the composition, G composed with F. So what you do is you just imagine just inputs and outputs. So this has to be a function defined on A cross C, right? So you go through the elements of A. So first of all, we have little a in A, and A takes F takes A to 0, and G takes 0 to 3. So we have A comma 3 here. And F takes B to 1, and C takes 1 to 1. So this is going to be B to 1. And F takes C to 0, and G takes 0 to 3. Okay, so that's our composition function there. Now here's an important theorem that links composition with the concepts of injectivity and surjectivity. If f is a function that takes A to B and g takes B to C, so if these functions are both injective or both surjective, then so is G composed with F. And so if F and G are both injective, so is the composition. If they're both surjective, so is the composition. And so it follows if F and G are both bijections, right? So they're both injective and surjective, then so is G composed with F. And the proof is quite simple, actually. So first suppose F and G are injective. Suppose F and G are injective, and that, so remember, how do you check injectivity? You check that if two things go to the same place, right, then those two things must both be equal. And so let's say G composed with F sends A and B to the same place, right? So you have two things in the domain going to the same place. Injective means that those two things must be equal. So we're going to look and see, hopefully A equals B somehow. Now, G composed with f of A and G composed with f of B, we can write this as G of f of A equals G of f of B. And so what we can do is, if we isolate the parts in here, right, so we have G of f of A and G of f of B, but G is injective, right? So G is sending both of these things to the same place, so they must be equal. But by injectivity of G, f of A equals f of B. Right, but now we just use the injectivity of f, right? We have f sending A and B to the same place, so A and B must be equal. But then by injectivity of f, A equals B. Okay, and that's what we had to prove that G composed with F is injective. So that completes the proof of injectivity. Now suppose F and G are surjective. And let Z be an element of C. All right, so we have to show that this Z in C gets hit by something in A under this composition. So, well, Z is in C and G is surjective as a function from B to C. So by surjectivity of G, there is a Y in B such that G of Y is equal to Z. All right, so now we have this Y in B, which maps over to Z, but that Y in B, because F is surjective, has to be hit by something in A. By surjectivity of F, there is an X in A such that F applied to X equals Y. Thus, and so we have G of Y equals Z, but Y is F of X. So thus, G of Y, which is F of X, equals Z, i.e. G composed with F takes X to Z. So that's our proof. Okay, so injectivity and surjectivity are preserved under composition as long as both functions involved have the properties. So I again want to talk generally about having a function from A to B. If we have a function from A to B, this is a relation from A to B, right? So it's a subset of A to B, A cross B. And we picture this as arrows connecting things from A to B. And one thing we can do with these arrows is flip them around and get a relation from B to A. So flip the arrows, and what we get is a relation from B to A. So now I have an arrow back like this. I have an arrow back like that. I have another arrow back like that. Right? So you can see from this that the relation you get when you flip the arrows is no longer a function. So this is not a function. So it might be the case that you get a function, and we'll talk a bit about that in a second, but just notice, at least in this particular case, it's not a function, so it's not necessarily the case that it's a function. So it's not necessarily a function. So this relation is called F inverse. Okay, so the relation F inverse is not necessarily a function. And F inverse it's defined as a subset of B cross A, right? So now we have arrows going from B to A. So F inverse is going to be a relation in B cross A. So it's the YX in B, in B cross A, such that XY is in F. Right, so there's now going to be, so basically this says there's now an arrow from Y to X where there was before an arrow from X to Y. Okay, so that's what this inverse relation says, and of course this is in B cross A. So the immediate question is, when is F inverse a function? So two considerations. So in order for F inverse to be a function, first of all, it needs to be defined at every point in B, right? So like in our picture here, for F inverse to be a function, it would need to be defined at this red point here, right? So how do we have an arrow coming out of that red point for F inverse? Well, if we had an arrow coming into it for F, right? So one thing we need is that we need F to be surjective, right? We need every point in B to be hit. We need an arrow coming into it so that F inverse now has an arrow going out of it, right? So F must be surjective. And two, well, we need exactly one arrow coming out of everything in B, right? So exactly one arrow coming out of everything in B for F inverse means exactly one arrow coming in for the function F, right, when we reverse the direction. So we see that F must be injective as well. So we find that F must be bijective. And in fact, this is an if and only if. So if our function F is bijective, then every point in B has an arrow coming into it and exactly one arrow coming into it, right? So when you flip that arrow around, you have an arrow coming out of everything in B and exactly one, and that's all we need for a function. Right? So in fact, this is an if and only if. Okay. So this is just so that's not a formal proof, but I'll just state it as a proposition that F inverse is a function if and only if F is bijective. So you can picture that basically like, so I'll just draw a small picture here. You'd have to have everything in B being hit and being hit exactly once. And so it needs to be bijective. And then so this is the picture of F, and the arrows going back, those arrows are F inverse. So you have F sort of going, so F goes, and so your F goes this way, and F inverse goes the other way. And so what you can observe about, so what we can do is we can compose the functions F and F inverse in two ways. So we can consider, right, since F is defined on A cross B and F inverse is defined on B cross A, right? So you have A matches A here and you have B matches B there. So you can compose them in two different ways. You can consider F inverse following F, and you can also consider F following F inverse. And if you just kind of look at this picture, when you start on the left in A and you go over to B, right, and then you follow that up by F inverse, you're just going back along the same arrow you came at. So you just end up where you started. And so these compositions, what you expect is that F inverse composed with F, that should be the set of, well, it takes your input X in A and it just sends it to the same input. So the output is the same as the input, right? Because you go over to where you got sent into B, but then you just follow the arrow right back. Right? So this is the X, comma X, such that X is in A. And F composed with F inverse, by the same type of reasoning, this is going to be the Y in Y, such that Y is in B. And since these are compositions, they're functions, and they have a special name. So this is called the identity function of A, and this is called the identity function of B. So in general, this just serves here as a definition of the identity function. So this is the identity function of A. So much for the generalities. As far as the particulars go, you've probably found inverse functions before. So just to kind of remind you how that works. So an example, so f of x equals x cubed plus 1 has an inverse. So how you think about this is you think about y is your output for this function. So your input is x, your output is y. And what the inverse does is it takes that output and sends it back to the input x. So what we want to do is send the output back to the input. So i.e. express x in terms of y. And so express that original input in terms of the output. So all we do is you can just solve this equation, right? So you very quickly find that x is equal to y minus 1's cube root. And then, so this is the expression that takes your y, what you originally thought of as the output, takes that y as input and gives you x as output. Right? So g of x, so you define g of x to be the cube root of x minus 1. Right? So this is now the inverse. So this is f inverse of x. So you can check that, so f inverse composed with f of x, this is f inverse of f of x, which is x cubed plus 1, and our expression here for f inverse is that we take that x cubed plus 1 and plug it in for the x. So you have x cubed plus 1 minus 1, and then the cube root of that, and of course you just end up with x. And so this is the identity function this is the identity function for r on x, and f composed with f inverse of x, f inverse, that's cube root of x minus 1, and then plugging that into f, cube root of x minus 1 cubed plus 1. That, of course, just leaves you with x, and again, that's the identity of r. One last example with just a little more complexity. Let's consider the function from z times z to itself, defined by taking the pair mn to m plus n, m plus 2n, that pair. So I claim that this function is bijective, and we can prove that by just finding the inverse. So we can find the inverse by if we set our output. So just as before, where we had we had this function x cubed plus 1, you set it equal to y, and you try to kind of invert that relation. You try to solve for y in terms of x. So here we'll take our m plus n, m plus 2n, set it equal to, say, pq, and try to invert the relation. So try to express m and n in terms of p and q. So we have that. This means that p equals m plus n, and q equals m plus 2n. So in particular, one thing we can do if we subtract so we take q minus p, we just get n, right? So n is equal to q minus p, or negative p plus q. And so how we can get m is we can cancel the n's. So what we can do is we can multiply this equation by 2, so times 2, and then subtract the two equations. So what we can do is we can look at 2p equals 2m plus 2n, and q equals m plus 2n, and then subtract 2p minus q, and we get m. So m is equal to 2p minus q, right? So we see that what we can do is we can define g of mn, right, to be, so now we just sort of interchange the roles of mn and pq. So this is going to be 2m minus n and minus m plus n. And then the composition of f and g you can check. So then what you want to do is check that that g composed with f, that's the identity on z times z, and that's also equal to f composed with g. And thus this function f is bijective because it has an inverse function. All right, that's all that we have time for.